So my name is Jasmine. I'm starting my fourth year as a physical theoretical physics student at University of Manchester.
Yes, I'm Rene Breton. I'm a professor of astrophysics at the Jodrell Bank Center for Astrophysics at the University of Manchester.
Awesome. So I'm going to just go right ahead and start with the questions. So my first question is related to the topic that we've been covering today. So we've been talking about the physics of the very big. So in science, we call this astrophysics, of course. So could you tell me what astrophysics is and what it means?
Yeah, so I guess astrophysics is the field of research that covers the study of the cosmos and everything in our universe, really. So it's pretty broad. But more generally, I suppose that typical astrophysicists work in some of the areas actually that we cover at Manchester, which are cosmology, which is the very sort of like largest scales of the universe, how it formed and evolved. Extragalactic astrophysics, which is can be quite far, but it's mostly galaxies basically, and the voids between them, their arrangement. Then there's also another branch that's more like galactic astrophysics, which is the study of our more like local neighborhood in the universe, our own galaxy, the stars that make it, the dust and clouds and particles that are inside it, and the different other bodies. And then there's more like solar astrophysics, which is our solar system planets and smaller bodies, the study of the sun as well, and to some extent also the Earth in the more like broader context than just as the Earth itself.
All right.
So these are the typical areas, of astrophysics.
Yeah. I mean, it's quite a broad field, isn't it? Yeah, we've been talking about stars in our presentations and stuff. So so what does your specific research do? What do you study?
So my research is primarily focused around the study of neutron stars and pulsars. So neutron stars are these small remnants of massive stars that were originally 8 times the mass of the sun or heavier, and exploded in supernovae. And then not the entire star, exploded and flew off, but the center, the core of the star, where the nuclear reactions were originally taking place and burning. It's now turned into a very small object, about 10 to 15 kilometers in radius. And that object is basically so dense that only neutrons are the main constituents of these bodies. So we call them neutron stars. Mm-hmm. And then there's a subset of these objects that we call pulsars. And they're the ones that we can see blinking in the sky. And that's because the majority of the light they produce comes from above the magnetic poles of the star. And that's related to the strong magnetic fields that they have, and only lets particles that are trapped in this sort of like giant magnet, escape along the poles. And as they escape, they produce radiation. So as the star rotates around its axis, if the poles are misaligned with the rotation axis, you're going to see, this sort of light beam sweeping across, just like a lighthouse. Mm-hmm. And so you see the blinking star, and that's why we call them pulsars, because that's a contraction of the word pulsating star.
All right.
And the vast majority we can observe in the radio regime, so with radio waves, such as with the Jodrell Bank telescopes, like the big Lovell telescopes, and also the smaller ones on site. But also there are some that are visible in other regions of the spectrum. So even at gamma rays, the highest energies.
Cool. That sounds really interesting. So if we go back to when you were a student, and you were studying physics, how did you decide to become an astrophysicist specifically?
Yeah, it's a good question. So actually, I've wanted to be an astronomer, since I was probably about 6, 7 years old.
Oh,
It, yeah, it's kind of this cute, romantic story of, the little kid, stargazing and wanting to become an astronomer and fulfilling, his wish. But it's not, necessarily the case, for my colleagues that surround me. But in a lot of cases, people are like, interested in physics and maths, and then they go to, undergrads, and then they choose a branch, and, it might be astrophysics or something else. For me, it was more the opposite. I started reading about, little books, for kids, about the planets and stuff. And then I was very curious. I was a Boy Scout, stargazing, it was really interesting in looking at the stars. And then I built a telescope with my dad and brother, and I joined astronomy societies, and then did science fairs and things like that. And that's what actually connected me to science. Because in the first place, I'm not from a family that, no one in my family has gone to university before me. So I was, the first. And, and most of the, people in my family, they're more like, sort of blue collars, working on like trade jobs and things like that. So it was a bit unusual for me. But that's what motivated me to go to university and do physics in the first place. And I wanted to keep my options open, but once I started studying physics, then I realized that astrophysics was really what I wanted to do. But as I'm sure you might have experienced, a lot of maybe you or your friends, you start a degree, you might want to do astrophysics, and then you realize, oh, actually, there's this other subfield or other thing that I'd like to do better now that I know more. But for me, it just stayed like that, and I just carried on.
that's so nice. Yeah, you're actually exactly right. So before my first year, I was enrolled on the physics with astrophysics degree. But then I think just a few weeks before the semester started, I was like, well, like reading about astrophysics, and I realized that wasn't like exactly what I was interested in, and I realized that I was more like inclined to the theoretical side of things. So I think it does kind of happen to a lot of people, like they just fall in love with space and stars, and it's just so cool, and then you realize that there's also these other parts of physics that are really cool as well. So I guess you've already kind of answered if you always wanted to become a physicist. So that's as long as you can remember, almost.
But I guess perhaps, for you, it's a bit, I guess you had a bit of a similar story, but slightly, opposite. But the thing that, sometimes people don't realize is that, being an astronomer is not necessarily how, amateur astronomy is, right? So it's not, I mean, we don't, put the eye, at the eyepiece and things like that, and it's really, the actual job is more like, the job of a physicist, writing computer codes, analyzing images, and, things like that. So and it really is, physics. So there are people who like the astronomy part of it, but, these days, especially, it really is astrophysics. So sometimes, once people get there, then they realize, okay, yeah, I don't like the actual physics part of the astronomy, and I like something else better. Or some other people, actually, they were not necessarily drawn into astronomy in the first place because they were not necessarily that interested, but actually once they start doing physics, then they realize, oh, that's the type of physics that actually connects to me.
Yeah, that sort of makes sense. So you kind of mentioned sort of non-experts doing astronomy and stuff. So do you have any sort of tips or examples of any books or other material that someone who doesn't have a formal education in physics could sort of gain that basic understanding of physics and space in general? Do you have any tips for that?
Yeah, well, so I would say, the way I started is probably what I would recommend to most people. So there's lots of magazines, for instance. I used to subscribe as a kid to Sky and Telescope and Astronomy, and also some French-speaking ones, actually, because that's my native language. and they tend to be quite good because they're quite they follow what's current, right? And then they have like in-depth articles, but they're always quite accessible. And initially one might not understand everything, but then you can build your knowledge, and there's quite a range of complexity in these magazines. And then reading popular astronomy books as well. So you see, not to do some marketing for my colleague Brian, but we all know of Brian Cox's and also Jeff Forshaw, right, who's co-writing them. But also there's a bunch of other books as well. I think to some extent they're all quite good to read. Arguably, it's all a bit about following your interests. So a lot of people, like myself, I started with more like astronautics first, like traveling to the moon and things like that, and then I kind of like expanded. So yeah, things like magazines, I would say they're pretty good now. These days with the internet, things are quite democratic because it's really easy to access information. But also, especially for the the younger audience, perhaps I would say do try and join like astronomy societies. They're really good because if you're home alone, you can do a lot. But usually these societies, they I usually go on almost like tours, like visit something like a dozen or so astronomy societies every year, or if not more. And so they tend to invite, professionals to give talks, and also non-professionals, like other amateurs from other clubs and such. And they're really good because you can really get and engage with others. They tend to be really nice at sharing also, and some will have access to either small observatories or small hardware like telescopes that you can borrow. They might have a subscription to a magazine, and then the magazines are there. You can just borrow for a couple of weeks, give it back. So they tend to be really nice, but I would say, sadly, it tends to be kind of like middle-aged, gray-haired, men who are at these societies, and I always feel that there should be more like younger people. Because they're interested as well, and these people are very welcoming, so they're really nice communities to join, and you can learn quite a lot from the more experienced people, and have access to resources and things that you would not otherwise. Typically, the main mistake I've seen, and I almost made it when I was a kid, is like, oh, I was a teenager, and then I was like, okay, I got a bit of money, and like Christmas is coming up, so I want a telescope. And then my parents were like, okay, well, let's go to the shop and try and buy you a telescope. And then I went to that really nice shop where and whatnot about what my goals were. And then he basically said, yeah, I'm not going to sell you a telescope actually today. And I was like, what? And he said, I think, for what you're doing, you'd rather, be best to learn all your constellations first, get a good binocular set and learn a bit more, because I suspect that, one of these sort of cheapo telescope is not going to be so good. You'll look at the moon a couple times and then you put it and it's just going to collect dust. And that was the best advice I've ever got, as a kid, because a year later, I was actually purchasing an actual mirror and built my own telescope, which, was 25 centimeter mirror. It was like something like, 3 times bigger than the typical things that people will buy. And it worked so much better and it came up cheaper. Yeah.
That's so cool. And I'm sure nowadays, especially like if you want to build your own, like just go to YouTube, like how to build your own telescope, and I'm sure you can find that there. That's great. So if we get back to your sort of day-to-day life as an astrophysicist, so could you describe to us what is your typical day like at your job?
Yeah, so I'll describe what my theoretical, perfect day would be like, because when you're a professor, actually, you do a lot of, people think like, okay, I'm just gonna sit like that, at my desk, and sort of eat my apple and think and stare at the ceiling. It doesn't quite happen that often these days. I tend to be quite busy doing, some admin, preparing teaching and things like that. But when I have a day that's quiet, right, and I can actually do research, then I think my life is more like an applied computer scientist to some extent. So the area of actual research I'm involved with is somewhere in between. I mean, you have theorists who do what I call hardcore theory, like they pretty much only need a pad and a pencil, and then they go and write equations and whatnot. Then you have the sort of like pure observers, right, at the very other end of the spectrum, who they collect data and they kind of curate it to some extent and do a bit of analysis, and then they kind of publish papers. It was more prevalent back in the days because basically, you could just stare and just publish, an image, and that was it. These days, you tend to need to do more, physics. But I sort of sit somewhere in between where I do some applied theory. So I tend to like use people's model, and then I turn them into, from the maths, I turn them into some kind of computer program that can simulate something, simulate some observations or some results that I would expect. And then I collect some data, and then I kind of like try to, see if the data match, the expectations that we have. So my main, focus is on trying to understand the physical limits of these pulsars, because, they're such extreme objects, they're very dense. And we don't know, for instance, how massive one can get before it would become too big and then have to turn into a black hole, because the gravity would be too strong to, hold it together as it is. So you can imagine that, I cannot just go with a scale and, measure the weight of the mass of a pulsar. So we use tricks that are, pretty much as old as, Newton himself, which is to use binary systems and use the laws of gravity and measure the orbits, and then use that to measure the masses. So I basically go and hunt for, binary systems that contain a pulsar, and then I measure, the pulsar motion, and I measure the companion's motion as well. Typically, the companion will be a small star, so you see it with like a, visible light with a more like conventional telescope. And so, so then so that's what I do. And I try to measure the masses and then use the models to, account for the data and also see, what works out. So the typical days would be, the sort of life cycle of my research would be, okay, we need to get data. So we need to write a proposal where we say which sources we'd like to observe and why, and we need to justify it. And then there's a deadline. It gets sent to a committee where peers, sometimes including myself, but obviously not reviewing my own proposals, will decide, which ones are best and which ones are accepted. And usually, there's a factor of between a few to something like 10 or 15 times more requests than available time on these facilities. So it's highly competitive. So if you're lucky and good enough, you get your observations accepted. And then eventually you either, go to the facility at the set time and observe, or these days, on bigger facilities, it tends to be done for you, given all the parameters. So you're gonna work, quite a bit of time as well, like setting all the technical details. And then eventually you come back home with the data, like on your drive or via internet or whatever, you get your data, and then you start, analyzing them with softwares. And then again, like, a lot of what I do is uses very non-standard analysis procedures. So I'm going to spend quite a long time actually writing software that can actually process the data. And then after that, it's all about, writing it up into an article that will be submitted in some specialist journal. And then it gets maybe accepted, or you have to revise, and then you start over. So that's sort of the cycle. So most of my days is basically, when I do research, is basically sitting and writing computer software where I analyze. But sometimes what people don't quite realize actually is that the initial processing and kind of looking at the image is to some extent the easy part. What really takes a long time is convincing yourself that the result you're getting is correct or incorrect, right? And because if you measure, let's say, I've done some research in the past where I would measure the motion of these bodies, and I would try and assess, whether the motion proceeds according to the rules set by general relativity, which is Einstein's, theory that explains, motion of and gravity. And so if you measure something, so if the measurement you make does not agree with, the theory, then you start asking yourself, well, okay, the theory has been out there for 100 years. Einstein was quite arguably much more clever than I am. So, was he wrong, or and am I right, or is it the other way around, right? And then if you measure something that also agrees with the expectations, then it's the same, right? You need to really evaluate, okay, well, does it agree just, by luck, and the theory is fine, or is that not correct? And you don't want to be biased by what, the initial hypothesis is, because it should just be, the data are there, they tell you something, and it should be, kind of independent of what your opinion is or what your expectation is. And that is really the toughest part, because ultimately it depends on, how much uncertainty and how much you think you understand the data. And you can spend an awful lot of time, doing that.
Yeah, that's really good that you explained sort of basically in essence the scientific method. And I feel like this is something that some people who are not involved in science, or they don't always understand this, and that in science it's a very rigorous method of checking if your observation or your result is actually correct, because there are so many, especially you mentioned you write code, I also do a lot of coding in theory, and there are so many things that can go wrong just in the code, and there are so many places where you can make a mistake that can then result in a false observation or something. So I think it's nice that you sort of explain that you yourself has to be your own critic almost, and you have to be well, what have I done wrong, or what have I done right? And that's a really good thing to explain to people, I think, because especially nowadays when I feel like there's more of a sort of, we're starting to question maybe some of our scientists a bit more. So I think it's good to sort of put that out there as well.
Yeah, I think sometimes people don't. So there are various reasons, right, where say some results or whatever can be wrong. So sometimes it is like a human error, right? Whereby there was a coding mistake somewhere. You put a number and then actually it was the wrong number by mistake or typo. And these, in general, we try to avoid them as much as possible, right? By having others look at our work. That's what part of the what we call the refereeing process, to publish as well is. But sometimes it's just bound to happen also occasionally that it is all still making it all the way through. But more and more we try to, for instance, in my group, we tend to make our data available, and also the relevant bits of code. So that's what we call open science, so that others can take it, right, and reanalyze and even build upon what we've done. So it's very helpful because sometimes people are reluctant to do that, but actually, because, they want to protect, kind of the work, but actually doing that actually brings feedback, but also helps, gives a bit of a safety, net to catch, some errors. But then there's obviously, some people are not well-intentioned, but I would say that in general, that's quite rare. I mean, there's always, a few scandals here and there, and like the whole of science, not astronomy in particular. But that is, very, very small, I would say. But then the other thing is just the data, right? I mean, sometimes you collect data, and for whatever reason, like there's something you just can't understand, with what you collected, that leads you to believe, some conclusion. And actually, when you collect more data later, with maybe a more sensitive telescope or something, then it shows that, oh, well, something that, seemed to be that way, actually, it's not the case, right? So, or sometimes, things can agree with a theory. And then when you have more precise instruments, then actually you realize that, oh, they don't agree, but that's just because, with the sort of typical accuracy you had, you could not tell the difference. So that's why Einstein's theory replaced, Newton's theory as like the more ultimate theory. But in day-to-day life, Newton's theory still kind of works really well. It's just that, to the very high precision, it doesn't account for everything.
That makes total sense. You mentioned also like that when you start your like sort of research process, you have to write a proposal, and then there's quite a lot of people wanting to obviously do their own project. And I guess what I'm trying to lead on is like, why is it so important for us to study astrophysics? And like how can the study of something in space help us in our day-to-day lives?
Yeah, well, that's always I guess, the one of the really big questions, especially for, the people who don't work in the field. But what's actually interesting is that, even when you work in the field, I don't work on faraway galaxies, right? So when I sit on committees that have to determine, which proposals are best, I mean, to some extent, I don't care about that research, right? And the people, they also need to articulate why it's important. Mm-hmm. Maybe not at the same level that, someone who, works in, I don't know, biology or completely outside of astrophysics would care to know, but still they need to articulate why it's important. And I think doing that actually is also a really good exercise, because, thinking why we're doing something instead of just doing something and kind of like, just because, is always a good thing. So for the sort of, the non-scientists or the non-astronomers, I think, astrophysics, I would say there's two main reasons for doing it. The first, is a bit more the more poetic, thing, is just, because we can, and because we are just like pushing the boundaries of our knowledge, right? So, and that's just human nature. So obviously, back in the Middle Ages, I mean, you could have like a few people who would be writers and write plays and do music and whatnot. And nowadays, it's the same. We can, I think we can afford in society to have a number of people who do certain things that don't necessarily appear as, completely essential, like producing food, or, saving people's life. Mm. But is important for the society as, a cultural thing, right? It's the same for music and arts, but also because there might be, outcomes later that we cannot tell. If Columbus had, sort of never gone, or he had gone and never, went back after, or people didn't follow through, then there would, it would have taken much longer, or we might never be aware that, there were people living in America. And, there would be completely two separate worlds, right, from Europe and in the Americas. So I think it's the same thing. So just pushing the boundaries. But then when you look a bit more, like about these unexpected outcomes, for instance, well, a lot of what I do, trying to measure these masses of pulsars, it actually, pertains directly to our understanding of nuclear force and particles, how they behave. So by learning more about it, actually, we can unlock some of the mysteries of the nuclear forces. And this is complementary science to what people do, for instance, in Geneva at the Large Hadron Collider, where they smash particles, they try to understand the fundamental forces. So you can attack, various physics problems and further our knowledge of the laws of physics in different ways. So a lot of astrophysics is like that, or understanding how the universe evolved. Now, some of it might not have like immediate applications, but at the same time, it drives technology and it drives the progress. Like Wi-Fi was invented by radio astronomers in the first place, like the protocol and everything, that was invented by radio astronomers. The techniques we use in medical imaging for like tomography, for instance, when people go and get a body scan, those imaging techniques, they were actually developed by radio astronomers as well in the first place, because to make an image of the sky with a radio telescope, it's not like, a camera, an optical camera where you have like some like little detectors and pixels. You need to use multiple telescopes that are working together as a synthesis camera. And the techniques are, the processing that's done is very similar to making scans for medical imaging. So astronomers came up with like the basis in the first place, developed it. Then it was taken over by people in medical fields, who then carried on, improving it massively. And actually, these days we actually interact with these people in the medical sciences, because the techniques of like cleaning the images and whatnot, have evolved so much in the medical field that actually now they're becoming relevant again for astronomy with the new era of instrument that we're about to use, like the square kilometer array. Mm-hmm. And if you look at this massive project, the radio telescope, the SKA, the amount of data that will be generated by these hundreds of radio dishes will be equivalent to something like several times the current global internet traffic. So we need like really advanced fiber optics, computers. As it is, our computers and storage are not sufficient to actually cope with the amount of data and processing that will be required. So we need this law that people call Moore's law, right, where the computers keep getting every couple of years the computers double in performance. We need that to sustain for the next decade or so, in order to have enough processing to handle our data. So in a way, our requirements drive these computing companies as well, or other technology companies, and to deliver for us, because we're in a way we're big customers. But at the same time, then this means that people would have better video games with better graphic cards and things like that, right? So it's all part of the same ecosystem.
Yeah, I think that's a really good answer, because like I feel like especially nowadays, like just because you do physics doesn't mean that when you become a researcher that you're only going to be working in strictly like a physics field. Like I feel like most of the research that is done is like to some level interdisciplinary, and that's like such a big part of science in general. And I feel like physicists especially, because like the skills we learn like from problem solving and stuff, that's really useful for other fields as well. And I think like the point you mentioned about technology evolving as well is like a really good example, because I think, wasn't it like with the like space missions when they started, like those also like that sort of brought us so many new technological like advances in, like you mentioned, in medical fields, which obviously is directly related to how we can treat illnesses and things. So I think it is definitely a really important part of like our culture, definitely. So you kind of already touched upon this. So like how do we study space, and we can't obviously like, you know, create a sun in our lab. So how can we do experiments in space, and how can we study the objects in space?
Mm-hmm. Yeah, I think a lot of astrophysics is almost like forensic science, because you know I mean, you cannot, I mean, you sort of have like something that's there, and you have like a limited amount of information about how it got there or and whatnot. So, and especially, you know, in astrophysics, you're very far away, also far removed. So, you know, typically you need to rely on like you know, the bulk properties of the objects you look at and what you can see from the outside, for instance, but then try to infer what's happening inside. So for, you know, stars like the sun, for instance, you know, they look like, you know, this sort of like giant sphere and kind of a bit, you know, boring maybe or not, but actually, you know, stars are, because they're made of gas and there's, you know, turbulence and, you know, convection inside of them and radiation being transmitted, they typically pulsate, right? So even the sun or the stars that seem fairly quiet, they all to some extent jiggle a little bit. And so these pulsations, they tend to be distributed in a certain way, a bit like you know, if you play on a tambourine or on a drum, where, you know, depending on how you hit it and how hard and whatnot, there's only certain what we call mode, so certain types of waves that are permitted, right? And you learn that, you know, as an undergraduate physics, right, students that you know, that. It's the same for guitars, right? Only waves that are, you know, where there's only a full wave or multiple integer number of waves, you know, within where the strings are held. So these combination of waves, they tell us about how the sound waves or the various, you know, pressure waves can propagate inside these stars. And you can learn about the interior composition, and if there's a change in like the structure, a change in boundary, you can learn about it. And that's the kind of things that, you know, were perfected with, you know, in seismology, for instance, in earth sciences, right? That's how we learn about the interior of the earth, you know, from earthquakes and even like just sending waves. So that's a way you can learn about inside stars. Typically, you know, most stars, you can measure the color, you can measure the luminosity, and then these days, thanks to some of the space missions like the Gaia mission, you can measure the distance to, you know, within quite some large scale in our galactic neighborhood. And once you have all of that, then you can look, you know, on the larger ensemble of stars, how their colors are, you know, are distributed. And for a given star, you often don't see much changes, right? Because they live like for millions, if not billions of years. But then you'll have stars that are similar, but different stages of their evolution. So it's trying to link all of that together. So things like that is what we use. Dynamics as well, right? With the simple motion in binary systems. So that's how we extract the physics. You can extract masses and things like that from orbit. When you're lucky, maybe one star passes in front of the other, you know, as they orbit each other. So therefore you have an eclipse. And then the duration will directly relate to how big the objects are, one compared to the other one, and you know, given their distance between them as well. So that's how you start, you know, unraveling the physical parameters of these objects, and then you can, you know, you can build your knowledge from there.
Cool. Yeah. Like, even though I've studied astrophysics at uni, I feel like I still don't quite like appreciate how many different methods there are actually to see these things in space. So what about in terms of discoveries? What in your opinion is the most important discovery we've done in astrophysics?
Oh, wow, that's
you can mention a few if you can't think of one.
That's a daunting question, but I would say, you know, in the last sort of decade or so, there's been a few, you know, very important discoveries. I think probably the most important one, I would argue, is the direct detection of gravitational waves that took place, you know, only a handful of years ago. And, you know, immediately the year after, right, people got the Nobel Prize of Physics for that discovery. And we knew that gravitational waves existed, that were predicted by Einstein himself in 1916. So 1 year basically after his original theory of relativity, the general relativity. And it took until the late 1970s, 79 if I recall, for actually pulsar astronomers, so people who work in my area, to confirm that they existed. And the gravitational waves are caused by, when mass moves in space, it basically creates a ripple, a bit like, if you move something like in water, a boat in water, it creates essentially some waves. And when objects orbit each other, they produce, these waves that propagate outward. And it drives energy out of the system. So typically, if the objects are close enough, then they can, the effect of gravity is larger, and then they can, eventually collapse, and merge. And so we've seen systems that, where they could be measured so well that you could see, these pulsars getting, closer from each other. So we knew they existed, and it was according to theory, but the actual wave itself was not detected, until 3 or 4 years ago. Mm-hmm. And that's a completely revolutionary, discovery, because it's not, the waves, it's not light. So everything we know about our universe, basically, in astronomy, is basically carried by photons, by particles of light, whether they are radio light or, gamma ray or visible or microwave, UV, X-rays. But these waves, they're literally ripples, in space-time, which, if one passes, will make me, look wider and taller, or the other way around. Except that, they're tiny effects, right? We're talking about, there's continuously, some background of waves like that pass, and, it's less than, like thousandths of the width of a proton, the sort of disturbances. So that's why, hopefully I don't look too distorted. So, it's just opening up a completely new branch of astrophysics, where we can witness black holes, neutron stars, pulsars, merging, and give us access to completely new, way to study our universe. So in my view, that's probably the latest, biggest discovery.
Yeah.
But then I would probably also argue that, after that, like another, fairly recent discovery is that of fast radio bursts, which is, closer to me, and even closer, because they're basically these like millisecond long, really bright radio flashes. And, they're just emitted like that. We don't know why. And they come from far away. And in recent years, we've established they come from, fairly distant galaxies. And just recently, we also discovered that some of these flashes actually repeat. So we know nothing about, much about them yet. So it's a bit equivalent to, if for people who follow astronomy, the gamma ray bursts, which were, very mysterious, in the sort of early 90s. And now, the gamma ray bursts are established actually to be, neutron stars that smash into each other for some types, and then some other ones are probably exploding stars. So these fast radio bursts, we don't know much about them. We don't know if there's many types or if they're all the same type, and for some reason some repeat, some don't. But it's opening, new opportunities for us as well, like to, discover maybe some wild objects or study, far away in our universe as well through these bursts. So that's really exciting, and a lot of people are working in that field these days. And it shows that our universe, right, is not static, right? Because we tend to think, oh yeah, stars, they live for so long, you're not going to witness, anything happening. But actually, when you look at the universe, very regularly, you take pictures of the sky very regularly, there's an awful lot changing. So this is what the next big step in astrophysics is not only to, see deeper and fainter and whatnot, but also is to see more frequently and on a smaller time scale, because there's a lot happening, and it, and so we unlock new mysteries this way.
That's so cool. That's amazing. I'm going to finish off with a little pop quiz from physics, so I hope you're ready. So we've asked you 2 questions, so it's
Okay.
not too bad. So you mentioned black holes, and we've kind of covered them in our presentation earlier. So do you know the film Interstellar?
Yes.
Yes. So there's a scene when one of the characters goes inside a black hole, and then he sort of is able to sort of go back in time, and time is sort of like a physical dimension in this black hole. And I wanted to ask you how sort of realistic that is, and what would actually happen if you did try to do that, if you tried to go into a black hole.
Yeah. Yeah. So the movie is quite, realistic because the original script, right, and the basic idea was written actually by an astrophysicist slash physicist, Kip Thorne, who actually was involved also with the detection of the gravitational waves I mentioned. So, these things, like, I don't want to reveal too much about the movie for those who haven't seen it, but, the tides and things that, and time, the concept of time that you see in the movie is very realistic. I think the idea, when you get into the black hole and what happens, with time and, maybe time traveling and whatnot is probably a bit more, like science fiction, in that sense. Because actually, and that's something, that, well, I'm loosely, studying is, the fact that, at very high gravity and very high densities and things like that, then you come to a point where you cannot explain, our laws of physics are not good enough to explain what happens, right? So, I can take a cannonball and shoot it, and I can describe the trajectory really well, or I can take a pulsar or black hole, make it orbit around another, understand well. But when you get to matter that's really, really dense, there's a point where all of our gravities, they fail, all of our theories, they fail. And that's why people think, that quantum theory, the theory of the very little, and gravity, according to general relativity, they must somehow meet up somewhere and, become one theory. But we don't have that theory yet. So when you get like to the, sort of inside the black hole kind of thing, you reach the point where, we cannot really predict, in a way that our theory allows us. So then you can maybe speculate as to what might happen, like, time might reverse, or there might be, some wild things. You might be able to travel through space really quickly through these wormholes. But the truth is, all of this is speculation. So I don't think it's necessarily completely impossible. Personally, I think it's a bit impossible for maybe a human to, sort of, travel, sort of through space like that. But a bit like you also see in Star Trek. But there might be ways for maybe information to travel or something, or maybe particles, but who knows? I would obviously be very excited to be proven wrong.
Yeah.
Yeah, but on the overall, I think, it's fairly, it's quite decent. Even the extrapolations they make are, they're not quite, they're a bit wild, but they, it's sort of things that we could believe, could exist perhaps.
Okay, good answer. So last question, why is space dark?
Why is space dark? Yeah. Actually, I would say space is not dark at all. It just sort of appears dark to us. So, on Earth, like the sky is blue because the light coming mostly from the sun, right, gets and it scatters off through a process that we call Rayleigh scattering, and basically it means that the more energetic the light, so the bluer the light, the more likely it gets scattered, and then it just ends up going in all directions, whereas the red light tends to carry on, in a more straight path. So it basically means that overall, the sunlight gets in all directions, and so you might, get some of the original blue light essentially getting back to you, but indirectly. So that's why the sky is blue. But once you go into space, because there aren't, it's basically empty. On average, between stars, there's about like 1 atom per, cubic centimeter, or so. So that's roughly the sort of the number of particles that you'll find in sort of interstellar space. So there's not enough of these to, scatter the particles all around and make, space look blue, for instance. But now there are particles coming from all around. And actually, if your eyes were capable of seeing other types of light, than just the visible light, and you could tune to other frequencies, then actually you would realize that space is like just amazingly bright. So with the visible light, you see stars. And actually, if our eyes were more, powerful to see, fainter stuff, if you look through the Milky Way, right, where most of the stars are, you would probably reach a point where, unless you can zoom in a lot, all the stars would, confuse, and then they just look like, this white cloud of like, just diffuse light from all these stars. And that's basically why, we see the Milky Way in the sky. But, if you look in radio light, for instance, I mean, all these particles in space, these charged particles like electrons, they tend to get captured by magnetic field and change direction, and these processes emit light. So our entire galaxy has like this big glow of radio light, and then fainter than that, especially in the microwaves, then the residual light from early in the universe, from the cosmic microwave background, as we call, like, is just ever present everywhere. So if you had like microwave eyes, you could also see this light that makes what we call the CMB. So space is not really dark in that sense. It's just that maybe we're not sensitive enough. We're not looking at the right place. Yeah.
All right. Great. I'll give you an A+ for your pop quiz. You passed. Right. So that's all the questions I had. Thank you so much.
I need to showcase my nice T-shirt. Which is from obviously the music aficionados. Well, I guess it should have been Blue Dot this weekend, so that's the Joy Division cover. Joy Division. This one comes from Japan, so that's why it's written in Japanese. But what you see there is actually the actual signal from the first pulsar that was discovered, CP 1919. So each line basically is a sequence where the pulsar spins and emits that beep, the sort of lighthouse, sweeping past us. So you have like the bloop, and then nothing, and then we just sort of stack them on top of each other. So that's why you have like this nice forest of pulses.
Yeah, that's really cool. I was going to mention that I really like the T-shirt.
Thank you.
Yeah, thanks so much, Rene, for taking the time to talk to us. And I hope all the best luck for your research, and hope you discover really cool things that we can read about in the future.